Hello champions, welcome to Diksha Karnataka YouTube channel. So if you are preparing for your KCET exam or PU board exam, then you must have heard about Wheatstone Bridge, which is one of the most important topic, and you think that it is only about a derivation and few numerical questions. So basically in today's session we are obviously going to do that, but before starting the topic, so here is under 30-minute important topics session that I am going to discuss, obviously the Wheatstone Bridge. Now before starting about Wheatstone Bridge, just to tell you briefly about the history of Wheatstone Bridge. It was understood that around 1830s there was a person called Samuel Hunter. He developed a specific design to measure unknown resistance. Later on it was popularized by Charles Wheatstone, and that's why today we call it Wheatstone Bridge. Even though he was someone who modified it and popularized it, he was not the original inventor of this design, right? So very interesting fact. So now talking about Wheatstone Bridge, it is a device to measure unknown resistances. Okay, now unknown resistances can be measured using Ohm's law, V is equal to IR. So you need a voltmeter, you need an ammeter. Now why do we not use that technique? So that is one important question that might come into your brain. So let us see what is the problem with our conventional method of V is equal to IR, or by measuring voltage and current. Okay, so instrument resistance. First of all, for theoretical purpose, we assume that all voltmeters have infinite resistance, for all ammeters have zero resistance, but in practical cases they do not. They have certain resistances, and that actually hampers your reading. So when you are doing an experiment, because basically it's an experimental design which is used extensively till a few years back as well. Okay, now also it is being used inside laboratories, but not so much in commercial cases. But yes, it was a very much popular topic, especially when we were using telegraphs. Okay, for sending telegraphs we need to have some certain resistances, and to measure resistances, Wheatstone Bridge is one of the most sought after design. Okay, there was one design called post office box which was based on this design. Okay, now instrument resistance, obviously V is equal to IR, voltmeter and ammeter, they have some resistance, and we need to measure the resistance as accurately as possible. So if you are using voltmeter and ammeter, your data, your value will not be super accurate, and that can lead to catastrophic failures, especially when you are using it for some very precise calculations, right? Deflection error, both values come from pointers on a scale. So when you are using voltmeter and ammeter, they have a scale, they point at certain point, and the deflection may not be accurate as it should have been. So that can also be cause errors. Okay, contact and lead resistance, that means when you are the contact points where you are connecting the voltmeter and ammeter, they also have certain resistances, and that's why the result that you are getting using a voltmeter and ammeter and using Ohm's law is not super accurate. So that's why we do not use V is equal to IR for measuring unknown resistances. So that's why we need a null method where even though we are using some meters, the resistance of those meters are not coming into picture. Okay, so instead of reading a value of a scale, we adjust the circuit until the galvanometer reads exactly 0. So the circuit we will see afterwards. There we have a certain arrangement where the galvanometer's requirement is only to show that the current is not flowing. That's it. That means no galvanometer resistance, no ammeter, voltmeter are required at all, and still we can measure unknown values, right? So that is the beauty of Wheatstone Bridge, and that's why it becomes so much popular. That is, even though we have voltmeter and ammeters and we can measure the current using them, but that is not popular because that has a lot of deficiency, lot of problems in their measurements. That's why even though the V is equal to IR was a very simple rule, it is actually a little bit of what should I say, paradoxical as well, because when you are measuring V is equal to IR, the resistance of galvanometers, the resistance of ammeters, everything is added into that R value. So unknown resistance, you are not getting the exact value of the unknown resistance. Yes, it will give you an approximate idea, but not the exact value. That's why V is equal to IR method is not compatible when it comes precision. When you want the value of resistance very much accurately, then it is failed. It actually fails. Now this is the design of Wheatstone Bridge. Here, as you can see, here we have, this is a diamond design. This is called diamond design, where we have 4 arms, okay, P, Q, R and S. 4 arms of a Wheatstone Bridge, and between these 4 arms there is a galvanometer is connected, and there is a cell which is sending a current, which is connected outside the diamond structure. Okay, so this is the main core design of the Wheatstone Bridge, and 4 resistances P, Q, R, S are connected. Generally, S is an unknown resistance, P, Q, R are known resistances. Okay, so AB is equal to P, BC is equal to Q are the ratio arms. EDR is a known variable resistance. So this one is actually a variable resistance. Variable resistance means you can vary its resistance. Okay, it is a variable resistance. Okay, and S is unknown resistance. So this value you are trying to find out. This one is unknown. This value you are trying to calculate. Okay, now battery diagonal. So a cell of EMF E and key K is connected across the diagonal AC. So this is connected like this, and galvanometer diagonal. Galvanometer is connected between B and D. Okay, R. Now what happened is that P and Q are fixed value. Okay, P and Q are PQ have fixed values. You vary R till the current through the galvanometer becomes 0. Okay, you vary this value R so that the current through the galvanometer becomes 0. Then using P and Q ratio, you can calculate R, and R value is also known, because you, even though you are varying it, you know its final value, and using the ratio you can calculate the unknown resistance. Now how to calculate the unknown resistance? Let's look into the formula. So the balancing condition for a Wheatstone Bridge, we will do the brief derivation as well. The derivation is very simple and easy. So if you are struggling with the derivation, don't worry, I will help you in that as well. So P by Q equals to R by S. This is the balanced condition of Wheatstone Bridge. So when they say that find the balanced condition of Wheatstone Bridge using Kirchhoff's laws, you have to finally show this ratio. You have to derive this ratio. Okay, and from here you can calculate the unknown resistance S. S is Q upon P into R. Okay, and this is the basically the foundation of many questions as well in a KCET exam and any other exam that you are writing. This is a foundation for questions as well. Now here, if you see this expression, there is no mention of EMF E of the cell. Also, there is no galvanometer constant G present in this equation. That means when you are using this method, the internal resistances, the cell value, the EMF of the cell, they do not matter as long as you are getting a result. That means you are getting a current that is sufficient. So weak battery also will suffice this experiment, right? So no EMF term is present here, no galvanometer constant is there, and it is basically a ratio and not a reading like you are reading from galvanometer or voltmeter. This is not a reading, this is a ratio. So if you know the ratio, you will be able to get the unknown resistance, right? Now let's move on with the next part, derivation. So as I mentioned, derivation also I will help you. Now while doing the derivation, you need to draw this circuit and you need to show certain things. For example, what are the currents? Say I1 is current through this junction, I2 current is passing through this, okay, I3 current is passing through this, and I4 current is passing through this, and the galvanometer current IG is passing through the galvanometer. Okay, so this is the structure. As total current is passing through this, you can show it, you may skip it, not required. Okay, now what? Now next part is no current flows through the galvanometer. So when the bridge is balanced, galvanometer current becomes 0. So if the bridge is not balanced, the galvanometer will show some deflection. The galvanometer meter will show some deflections stating that okay, current is not 0. Your whole one and only purpose is to vary this unknown resistance, this variable resistance, so that the galvanometer current becomes 0. So when the galvanometer current becomes 0, the needle of the galvanometer shows 0. That means galvanometer is no current is passing through the galvanometer. That means the bridge is balanced. Okay, so this is the galvanometer. Generally galvanometer shows a reading like this: 1 2 3 4 5, 1 2 3 4 5. Generally this is how the galvanometer looks. Okay, if you are doing experiment in a laboratory, later on you will see this. Okay, so this is a galvanometer, basic structure of galvanometer. I am not very good at drawing, so please pardon me. Anyway, so when the galvanometer shows 0, that means the bridge is balanced, and that means Ig is equals to 0. So you have to apply Kirchhoff's laws in two different loops. What are the loops? First, you have to apply Kirchhoff's law in loop AB, ABDA. So this is loop number 1, ABDA. So this is your loop number 1, and next loop is BCDB. This is loop number 2. Okay, BCDB and ABDA. So these are the two loops. So if you apply loop rule for ABDA, you get I1P minus I2R minus IGG equals to 0. So from here you get I1P is equal to I2R, and from the second loop you get I1Q is equal to I2S. Okay. Now I think yes. So if you apply this, you will get these two conditions. Basically, when the Ig is 0, that means what? That means if I think there is a small correction here. It should be 2. It should be. So say this is your I2. This is your I3. This is I4. Now when the Ig is equals to 0, when Ig equals to 0, then whatever current is passing through this junction, this arm, that definitely should pass through the other wire as well. So we can say I1 must be equals to I3 and I2 must be equals to I4, right? So because no current is getting deducted or no current getting added, that means if 2 ampere current is passing through this P, the same 2 ampere has to pass through Q as well, because Ig is 0, right? Now that's why this derivation is very easy. Okay, same current through P and Q and same current through R and S. That means I1 and I2 are only two currents that you need to consider. Now if you take the ratio of these two equations, you get P upon Q equals to R upon S. Okay, easy derivation, very simple. If you just remember these steps, your 5 marks in Q board will be secured, because there is a high chance this year this will be coming as a 5-mark derivation. Okay. Now one more important point is that, so this is a very symmetric circuit. So in case of symmetric circuit, swapping the galvanometer and battery does not change the balanced condition. There was a MCQ question in the past that if you swap galvanometer and cell, what will happen to the balanced condition? The balanced condition will remain unchanged. It will not depend on the relative position of the E and G. Even if you put the E over here and G outside, you will still get the same condition, that is P upon Q equals to R upon S. The balance condition does not change on swapping galvanometer and cell. Okay. Now, next is 4 things examiners love to test. Okay. So what kind of questions might be asking? Sensitivity. The bridge is most sensitive when all 4 resistances are of the same order of magnitude. Arms differing widely give a sluggish, unreliable null. Okay. So if the all 4 resistances are almost of the same order, for example, if you are using, say if you are measuring your unknown resistance is say 50 ohm, then everything should be very close to 50 ohm. Then you will get a better null point. Your result will be more realistic, I will say. Okay, if your unknown resistance is 50 ohm and if your P and Q say 500 ohm, then you might not get a very good null point. Okay, your result, you instead of getting 50 ohm, you might get a value say of the order of say 45 to 55. Anything between these two you might get. You will not get exact 50 ohm as an answer. Okay, that is one. Now unbalanced bridge, if P and Q is not equals to R by S, current flows through G, the direction of deflection tells you that this is you have to adjust R, the bridge is not balanced. Now based on unbalanced bridge, there was a numerical question came only once in 2024, if I remember, or 2025. Okay, if you want the numerical questions based on unbalanced Wheatstone bridge, please mention that in the comment section below. I want unbalanced Wheatstone bridge problems. So maybe next episode of revision under 30 minutes, I might solve few numerical questions from the topic Wheatstone bridge of unbalanced Wheatstone bridge, how to solve it. Right. Now cell and galvanometer, as I mentioned, interchanging cells and battery does not change. Next, balanced Wheatstone bridge, very important point. At balanced condition, no current passes through the galvanometer, so only galvanometer arm carries zero current. Okay, so at balanced condition, galvanometer arm does not have any current. So based on these four concepts, okay, you might see some questions being asked in exam. Okay, so that is very, very important. Okay. Now at balanced condition, another important point here, at the balanced condition, if you consider the balanced condition of Wheatstone bridge, okay, no current passes through the galvanometer, so you basically delete the galvanometer. Galvanometer is no longer required. You just consider this resistance P, Q, let me draw it. So P, Q, R and S. You can completely ignore the galvanometer, only this circuit is sufficient. So this is P and Q are in series, they are in series, okay, and this combination is connected in parallel. R and S is also in series and their mutual condition is parallel. Okay, so PQ in series, R and S in series, and their mutual condition is parallel. So that's how you should approach a balanced Wheatstone bridge. We will solve some questions on balanced Wheatstone bridge, obviously. MCQ questions, that is very important point to remember, that at balanced condition, why balanced condition is super important, because at balanced condition you basically remove the galvanometer. Galvanometer is no longer required in the circuit, no current passes through it. Why do we keep a galvanometer, right? That is one of the beauty of this system. Okay, now some of the applications of Wheatstone bridge. Now one of the application was Metre bridge. Metre bridge is used to measure length per resistance per unit length, which is no longer part of the syllabus. So that is one application. Other than that, strain gauges, a metal foil grid glued to beam changes resistance at stretches. One arm of the bridge is the gauge. Okay, load cells, 4 strain gauges of the 4 arms of the bridge give the reading of a digital weighing machine. So that is one another application. Thermistors and RTDs. Okay, resistance varies with temperature, so off balance voltage becomes a temperature reading. So basically you can measure temperatures using changing resistances, so that can be done using Wheatstone bridge. Okay, light sensors, if light falls on certain materials, their resistance changes, and based on that resistance change you can actually measure how much light is there. Okay, so light meters you may have seen being used in cricket matches, okay, especially in test crickets. They used to measure light sensor. So even though the technology is slightly different, but you can design a Wheatstone bridge based light sensor as well. Okay, so there are few things using that you can actually measure the change in resistance, and based on that you can say that okay, temperature is how much, light is how much, so etc. Are being done using Wheatstone bridge. So Wheatstone bridge is one of the most applied technology in our life. Okay, one of the most, not obviously the most, but one of the most applied technology in our life. Now as I mentioned, balanced condition for Wheatstone bridge, this is Wheatstone bridge at one glance. P by Q is equal to R by S, and equivalent from P into S is equal to Q into R. Okay, S equals to R into Q upon P. Okay, if balanced, G arm carries no current, so G arm can be removed. G arm means galvanometer arm. Okay, so galvanometer arm can be removed if no current, if the bridge is balanced. Okay, now let's see 5 KCET level question. I think the options are, this question is slightly small, so this is 4, this is 12, this is 6, and this is 16. All of them are ohms. Okay, I am writing it hand because obviously the text is not appearing properly. Let's see. In a balanced Wheatstone bridge, the resistances in the arm AB, BC and AD are 6, 4, 6 and 8 respectively. The resistance of the arm DC is. So what are the arms? So here the arms are given. Always remember it is A, B, C, D. This is the arm structure for a Wheatstone bridge. Standard arm structure is A, B, C, D. So A, B, C and AD are given. So AB is 4, BC is 6. AB is 4, BC is 6. Okay, AD is given as 8. AD is given as 8, and they are asking what is the resistance of DC. Okay, what is the resistance of DC? So we know that in balanced condition 4 by 6 must be is equal to 8 upon S. This is S, unknown resistance S. Okay, P by Q is equal to R by S. So using that you can calculate S. S equals to 8 into 6 by 4. Okay, cross multiply. So this S comes up, this 4 comes down, and 6 goes up. Cross multiplication basically, right? So 4 2s are 8, and you get 12 ohm. So the resistance of unknown must be 12 ohm. Okay, so the correct answer for this question is option C. Now next question is, a Wheatstone bridge is balanced if the positions of the cell and the galvanometer are now interchanged. Then the bridge becomes unbalanced, the bridge remains balanced, the galvanometer is damaged, the current through the cell becomes 0. So as I mentioned during my session, that even if you interchange the cell and the galvanometer, if the bridge is balanced, it will remain balanced. So that means the bridge remains balanced, right? Now next is a circuit based question. So if you see that the network shown, the equivalent resistance between A and C. So equivalent resistance between A and C. So this is the Wheatstone bridge structure. If you see 10 10 10 10, all the resistances are same. So definitely it's a balanced Wheatstone bridge. So in case of balanced Wheatstone bridge, we do not consider the galvanometer. Galvanometer can be removed, and we will get a circuit like this. So where we have a 10 ohm here, a 10 ohm here, a 10 ohm here, and a 10 ohm here. Okay, so this is my A, this is my C. Okay, so 10 10 10 10. So two 10s are in series, so their equivalent resistance will be, so basically you can erase it, you get, okay, two 10s are in series, so I know it will be 20 ohm. Okay, here also two 10s are in series, so their equivalent resistance will be 20 ohm. Now two 20s are in parallel, so what will be the equivalent resistance? So when two equal resistances are connected in parallel, their equivalent resistance is R by 2, so that is 10 ohm. So the equivalent resistance of the combination is 10 ohm. Now this is a shortcut that you should remember if you see this kind of questions where all the resistances are same in a Wheatstone bridge design, then the equivalent resistance will always be equal to one of the resistances. So if all of them are R, then equivalent resistance will be R. If all of them are 2R, equivalent resistance will be 2R. Okay. Now there is one more design that can be asked in KCET exam. It was asked, but it was not coming last few years. I think 2024 there was a last question based on this design. So this is one of the design. Okay, so you have to remember this is also a Wheatstone bridge. This is also a Wheatstone bridge. So all of them generally given R, 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 R. Now here this portion is the galvanometer. This is the galvanometer. The complicated portion which appears to be out of place, this is the galvanometer. If you stretch these 2 points, you will get the Wheatstone bridge design, the diamond design. But this is also a Wheatstone bridge design. Okay, and if the bridge is balanced, definitely you can erase this portion, and you will see that so same structure you will get. So this is, these two are in series, these two are in series. So overall resistance you will still get as R only. Okay, so this is also same circuit, Wheatstone bridge circuit. So if the question is being asked like this, also need to remember the equivalent resistance is R, nothing else, right? Let's move on with one more question. The bridges shown is not balanced. The value of S that will balance it. So here 638 S is given, and they are saying that what will be the value of S so that the bridge becomes balanced. So here again, what is the rule? 6 by 3 equals 8 by S. So here you can cancel 2. So S becomes 8 by 2, that is 4. Okay, so the value of S must be 4 ohm. Value of S must be 4 ohm. So another question, and if you see similar questions, you should be able to solve it, right? Now let's move on with another question. In a Wheatstone bridge, P is equal to 10, Q is equal to 20, R is equal to 15, S equals to 20 ohm. To balance the bridge, the resistance to be connected in parallel with R. So here we are adding a resistance in parallel with our, in exam might be they are saying parallel or series, that also may not be given to you. They might say the resistance that has to be connected, this ohm parallel, this ohm series, like that. Okay, so you have to be careful and you have to check how much resistance you need to change. Anyway, so for balanced condition of Wheatstone bridge, we know that P upon Q equals to R upon S. So because we are adding a resistance to R, we will keep it blank for now. We will use other resistances P, Q and S. Okay, P is 10, Q is 20. P is 10, Q is 20, R is, we are trying to find out, and S is also 20, right? S is also 20 ohm. Now obviously 20 cancels and you get R equals to 10 ohm. Okay, now the given value of R, so this is say R dash, this is say R dash. Okay, given value of R was 15 ohm. Now we have to reduce it to 10 ohm. How can we reduce a resistance? By connecting something in parallel. Suppose the value of resistance that we are connecting in parallel is given by X. So we know that two resistances connected in parallel is Rx by R plus X. This is the equivalent resistance. This must be the equivalent resistance, right? R dash must be the equivalent resistance, so that when X is connected in parallel, we are going to get the value of balanced condition, right? Now that is 10, 15x by 15 plus x. Obviously you have to simplify this and find the value of x. So 150 plus 10x equals to 15x, or 150 equals to 15x minus 10x equals to 5x. So 5x equals to 150, or x equals to 150 by 5, that is 30 ohm. So you have to connect 30 ohm in parallel. You have to connect 30 ohm in parallel to get the balanced Wheatstone bridge. Okay, so this is the end of the question answer session. Now let us look into the summary of the chapter. So the Wheatstone bridge measures resistance by null method, so that answer depends only depends on neither of the cell nor the galvanometer. At balanced condition, P by Q is equal to R by S. So you can also remember PS equals to QR. Okay, before reducing any network, test whether PS equals to QR is valid or not. In real instruments, the bridge is deliberately run slightly out of balance, and the out of balance voltage is the signal. Okay, so that is one way of doing it. Now obviously you can practice these are the homework question. NCERT chapter 3, example 3.5 and exercise 3.22. These are the two homework questions that I am giving it to you. Okay, derive the balance condition. Obviously I have done it. Now if you want to download the PDFs of this lecture or any other lecture that we are doing on our channel, then you have to do one very important thing. Come to our channel, in our YouTube channel. Okay, you have to click on below at the description section of this video, click on read more, and there you will see that free ACE KCET 2027 course. Click here, you will be redirected to this page, and here you have to click on buy now, register yourself using your mobile number and certain basic details. Once the registration process is completed, you will receive an OTP. Using the OTP, you will log in to this course, and you will get all the lectures that we are doing in our different series. Everything is available over here. Okay, you will get the chapter wise contents exactly the way it should have been in this portion. You will get everything listed over here, right? So that is one very important point for all of you, those who are preparing for KCET or PUC. Every lecture notes will be available through this session only, right? So all the best for your KCET preparation. I'll be back with more chapters, and as I mentioned, if you want to know more about unbalanced Wheatstone bridge, how to solve problems based on unbalanced Wheatstone bridge, do mention that in the comment section below, and obviously subscribe to our channel. Till then, bye.